No, I'll stand, move around, maybe I keep it here. Yeah, use this. Yes. Shall we start? Yeah, pen drive I don't need. Yeah. Okay, good morning. Let's get started. Yesterday we started learning the basics of magnetism. So, we learnt that charges in motion produce magnetic field. Okay. So, whether you send a current through a wire, or you send a current through a coil, or you send a current through a coil with a electromagnetic core, ferromagnetic core, you can produce magnetic field. So, you can produce different amount of magnetic field depending on the strength of the current, the windings of the coil, and whether you have a ferromagnetic core with a permeability mu r. So, we learned that this mu r can enhance the magnetic field produced by a certain current in a coil. Okay. So, this is the first concept that we learned. Then secondly, we started learning about different materials. So, I told you that in layman term there are only two types of materials. So, layman calls magnetic when a material gets attracted to a magnet, and if the material does not get attracted, a layman call non-magnetic. But physicists have different classification. So, the magnetic materials that get attracted to magnets belong to two types, ferro and ferrimagnets, and the materials that do not strongly get attracted or repelled, which are non-magnetic, belong to three types. According to recent science, there are four types. So, the fourth type I will teach you later, maybe towards the end of the class. Okay, one is diamagnetic. Diamagnetic materials are weakly repelled by magnets. So, which I demonstrated by the frog floating video. And you can also experiment by having a small water beaker and try to repel with magnet. So, that is one type. Then we have paramagnetic, which are weakly attracted by magnets. Then the third class is antiferromagnetic materials. Okay. So, this is something that we learnt. Then we learned to understand what causes these properties. Okay. So, why certain materials are ferro or ferrimagnetic, why some materials are antiferro, and so on. Okay. So, to this, for explaining that, I introduced you the concept of magnetic moment. So, electrons as such have two magnetic moments. One is when they are going around the nucleus, they have orbital magnetic moment. And secondly, because of the inherent quantum mechanical nature, for which I cannot give you any analogy, the electrons also have a spin magnetic moment. Okay. So, we have these two properties, and I told you that in materials like iron, cobalt, nickel, when you place them in a solid state, the orbital moment is quenched, basically it is 0, no contribution. So, it is the spin that will finally give rise to the atomic magnetic moments. It is not just spin, it is the uncompensated spin. So far, any questions before I erase? Okay, if not, let me erase this. So, I started with a simple explanation based on iron atom, isolated iron atom. It has 26 electrons. So, if you start with 1s and all the way to 4s, there will be 20 electrons. Then the next 6 electrons will be filled in 3D shell. Okay. So, we have 5 upspin, 5 electrons with upspin and 1 electron with downspin. This gives rise to a net magnetic moment of 4 Bohr magneton per atom. Okay. So, this is something that we learned first. So, first concept is the atomic magnetic moment. In fact, many other elements like chromium, manganese also have around 5 Bohr magneton per atom, but they are not ferromagnetic. So, it is not enough that the atom should have atomic magnetic moment. There is also something else that comes into picture, and that determines whether a material is ferromagnetic or antiferromagnetic or ferrimagnetic, and that is called exchange coupling, exchange integral, introduced by Heisenberg. So, Heisenberg proposed that when you have a system, the energy between two spins will depend on the exchange integral J. Okay. So, if you have two spins, these two spins will be parallel if J is positive. Okay, these two spins will be anti-parallel if J is negative. Okay. So, we learned that in ferromagnetic materials J is positive. So, all the neighboring spins of ferromagnetic materials will be parallel to each other, and in antiferromagnetic materials J is negative and your neighboring spins are anti-parallel to each other. Okay. Then we also learned the third, a subsection of antiferromagnetic material, where you have two neighboring atoms with the antiparallel spins. but one of them have a larger magnetic moment than the other, which gives rise to ferrimagnetic property. Okay, so this is ferro, this is antiferro, and the third one is ferrimagnetic. So, these are called ordered magnetic materials. Okay, any questions so far? Pardon? Yeah, is energy, yes. I mean, there are some cases you will have this kind of formalism. It's okay. You are only comparing, like let us say you have. There will be some cases where you will encounter this situation. Do you have any answer? Yeah, you. Yeah.
That is the quantum correction in Hamiltonian. The potential and the kinetic energy plus magnetic energy. So, negative of this magnetic energy will minimize the minimum if that's first to the magnetic energy. So, that's why the E should always be in such a way negative total energy.
Yeah, let us say you have some energy term where there is something else, then you have this, yeah, something I can say. Okay, so after this we moved on to learn about how do we measure magnetic properties. So, we know that ferro and ferromagnetic materials you can test just by checking whether the magnets stick to the material or not, but in the case of paramagnetic or diamagnetic antiferromagnetic material, you cannot see any interaction between magnet and your material. So, people physicists use precise measurements, right. So, we rely on magnetometers like VSM or PPMS, those kind of things, where we can measure the magnetic property, particularly magnetic moment or magnetization as a function of magnetic field. Okay. So, particularly vibrating sample magnetometer relies on Faraday's law of induction, which states that if there is a time varying magnetic flux and if you have a pickup coil next to this vicinity, then the pickup coil will pick up a voltage which is proportional to the time varying magnetic flux. So, this magnetic flux comes from your sample, because you are vibrating your sample, but the pickup coil is fixed, your sample is vibrating. So, the flux produced by this sample will vary as a function of time with respect to the pickup coil. So, you will see a voltage. So, once you know the voltage, you can convert this into magnetic moment, okay, by sweeping the magnetic field by using an electromagnet. You can measure magnetization as a function of magnetic field. Okay. So, if you do this for paramagnetic materials, the magnetization will increase linearly with respect to magnetic field, and the path for going up and coming down are 0, the same. So, paramagnetic material will have positive slope, and this slope is called susceptibility. So, we can say positive susceptibility, and if you take diamagnetic material, so this MH curve will show a negative slope, and again the path is the same whether you go this way or the other way. So, diamagnetic materials have negative susceptibility. And I also told you that if you want to distinguish between paramagnet versus antiferromagnetic material, you have to measure the chi as a function of temperature. So, basically you are looking at this slope for many different temperatures. So, if your chi is going like this, exhibiting 1 over T behavior, this is an indication of paramagnetism. And for diamagnetism, the susceptibility is independent of temperature, negative, whereas in the case of antiferromagnetic material, you will see a peak, then beyond which you will see this 1 over T behavior. That means, above this temperature antiferromagnetic material is paramagnetic, and here it is antiferromagnetic. Okay. So, this temperature, this critical temperature above which it becomes paramagnetic is called Néel temperature. Okay. Any questions so far? Okay, then we moved on to discuss ferro or ferrimagnetic materials. So, in ferro or ferrimagnetic materials, let us say you want to measure the magnetization as a function of applied field. The magnetization will not increase linearly, it will go non-linearly and saturate at certain field. And when you reduce the magnetic field, it will not follow the same path, but it will follow different path, and it may retain some of the magnetization. So, in all the other cases before, whether it is diamagnetic or paramagnetic, antiferromagnetic materials, all those magnetic materials will have almost 0 magnetic moment at 0 field. Okay, only ferromagnetic materials can retain magnetization at 0 magnetic field. Okay, then if you reduce the magnetic field, change the direction, increase the magnitude, it follows a different path. Okay, if you do this again, it follows another path. Okay. So, this property is called hysteresis loop, and we learned a few concepts like saturation magnetization, remnant magnetization, coercivity, and say saturation field and so on. Okay, so, these are important parameters related to a ferromagnetic material. And ferrimagnetic materials also will have similar hysteresis loop. There was a question about how do we distinguish between ferro and ferrimagnetic materials based on hysteresis loop. I have not answered, maybe I will answer another time. Okay. So, based on the hysteresis loop, now we can measure MS, MR, coercivity and so on. So, depending on the value of these parameters, we can classify materials, ferromagnetic materials or ferrimagnetic materials into two types, hard or soft. Okay. Hard magnetic materials usually have large permanent magnetization with respect to say ms, we can say large Mr over ms. They have large coercivity, ms may be moderate, whereas soft magnetic materials usually have a large ms, but they have a small Mr with respect to ms, and they have a small coercivity. So, both type are useful. So, some of for example, soft magnetic materials have their own use in transformers, in the writing heads of hard disk drive, and in electromagnets. All these applications you need soft magnetic material. Okay. Hard magnetic materials, because they can retain the magnetic polarity. So, you can use them in motor and any application where you need a permanent magnet, and you can use these materials for storage, memory. So, if you take modern automobiles, right, it is said to be that the modern automobiles have thousands of permanent magnets in different places. For example, you have say wiper, or you have steering, power steering. So many places you will find permanent magnet in an automobile. Okay, this is a huge market. China is holding a large economic value in permanent magnet. So, similarly, soft magnetic materials will have like transformer, electromagnet, and so on. Okay, so, this is where we stopped. So, when we were doing this, there was a question, what is the origin of these properties? So, why some materials are hard, why some materials are soft? Okay, this we haven't discussed. Okay, so, today we will start from here. Okay, so, the origin for the hard or soft magnetic property of a material comes from this property called anisotropy. Okay. Okay. So, before I say anisotropy, let me discuss isotropy. Suppose you measure a physical property at different direction. Let us say this is a piece of material, and you want to measure the resistivity of this material. Let us say this is a piece of copper block, and you want to measure the resistivity of copper. Okay. Let us say at first you send current in this direction, you measure the resistivity, you measure you send current along this direction, you measure the resistivity. So, you will find the value to be the same. Okay. Resistivity of the copper is the same irrespective of the direction in which you measure the property. Okay. So, these kind of properties are called isotropic. That means, the measured property is the same when you measure in different direction. Okay. So, when we say anisotropy, it is the opposite of isotropy. Okay. So, anisotropy means the property that you measure will depend on the direction in which you measure. Okay. So, that is basically anisotropy. So, when we talk about magnetic anisotropy, we are talking about the magnetic property being different depending on the direction in which you measure. Okay. So, let us take a few cases. Let us take let us say this is a piece of magnetic material you have. Okay. So, in this material, for example, if I measure hysteresis loop along this direction or I measure hysteresis loop along in the other direction. If the hysteresis loop is different in two directions, we can say that this material has anisotropy within this plane itself. So, we are measuring the property within this plane, but only the direction is different, either along x or along the y direction, but the properties are different. Okay. So, that is what I have shown here. So, for example, in one direction you may be easily achieve saturation. Easily means with very small magnetic field you may be able to achieve saturation. So, let us say I am applying a magnetic field along the x direction. Let us say this is the x direction, and I am measuring the magnetization as a function of time. Okay, let us say it goes like this. Now, I am doing the same measurement on the same sample. Now, I am applying magnetic field along the y direction, which is along the shorter length. Okay. Now, my hysteresis loop, look, let us say something like this. Okay. So, you can notice a few differences, right. Firstly, in the case of x direction, I needed a much smaller field. So, within this field I can reach saturation. So, somewhere here I can reach saturation, whereas in the case of y direction I need much more magnetic field to reach saturation. That is one thing that you see. Secondly, you look at the remanence is low in the y direction and it is high in the x direction. Okay. So, you can see a few differences in the properties. It is the same material, but only you are measuring the property in two different directions, and the hysteresis loop look different. Okay. So, this property is called anisotropy. That means, the property of the material that you measure depends on the direction. So, it is a direction dependent property. So, then we call it an anisotropy. Okay. So, in some materials you can have this kind of anisotropy. That means, in one direction, I mean within the same plane. So, here I am measuring the magnetic properties of the film in the plane, okay, by applying magnetic field parallel to the plane. Okay. So, in plane itself there are two directions. One easy direction is the one where you can achieve saturation easily. So, the red is the easy direction and blue is the hard direction. Hard direction means you need more magnetic field to saturate. Easy direction means you need less magnetic field to saturate. Okay. So, you can see the differences in the property. So, this is happening within the plane. So, we call it in plane magnetic anisotropy. Then let us take another piece of sample. Let us say another piece of sample is a different type of sample from what we have here. So, in this case, let us say I apply magnetic field perpendicular to the direction. So, my magnetic field is along this direction. I am measuring hysteresis loop perpendicular to the plane of the sample. Okay. So, in the perpendicular direction, now we perpendicular direction is Z, right. So, in the perpendicular direction I can easily saturate the sample with a very small magnetic field, and I can retain a large amount of magnetization even after I remove the field. So, we can call the z direction as the easy direction, whereas if I apply magnetic field along the x direction or y direction, I find that okay. So, remember in the when I apply magnetic field in the z direction, I can easily saturate, I can retain lot of magnetization. On the other hand, if I apply magnetic field in the x direction or y direction, I need more magnetic field and I cannot retain much of the magnetization. Okay. So, now we can say the perpendicular direction is the easy direction and the plane direction or the hard directions. Okay. So, if you have that property, for example, the measurement along the perpendicular direction gives rise to easier saturation, larger retention of magnetization, but within the plane it is difficult to saturate the magnetic field. Then we say that this material has a perpendicular magnetic anisotropy. Okay. So, people use the word acronym PMA to represent perpendicular magnetic anisotropy. Okay. So, let us consider some analogy. Okay. I have already described what is anisotropy, but I will try to give this analogy so that you can remember it better. Okay. Let us say you have a huge plateau which has this shape. Okay, is a plane. Okay, you have a car. So, you try to drive your car along say x direction, y direction, any direction, you will find no difference. Okay, this is a flat area, flat terrain. So, whether you go from here to here or here to here, you will you will press the accelerator almost the same amount, let us say 2000 rpm, then you can reach the same distance in different directions when the plane is like this, okay, and the terrain is like this. Okay. So, if you have a open flat ground, driving a car in any direction will be almost identical, you will find no difference. Okay. So, we can say this is an analogy for isotropy. So, whether you drive any direction, you will find it similar. So, that is isotropy. Now, let us say you have a scenario like this. Okay. You have a road which looks like this. Okay. So, in this case, let us say you want to drive from here to here towards me. Okay. You will find it easy, okay, because it is a straight road, right. You will find it easy, no problem. On the other hand, if you have to drive along this direction, okay, you need to press the accelerator a lot. Okay. So, you will find one of the direction to be difficult. So, this is hard, this will be easy. Okay. So, here you press 1000 rpm acceleration, also you can just move, but here maybe you need 2000 rpm in the first gear and so on. You will find it hard here, easy here. Okay. So, you can say this kind of road is anisotropic. Okay. So, you find it different in different direction. So, that is the analogy for whether you can saturate with a lower field or you need very high field. Okay. So, that is one definition of easy and hard direction. The second definition is about retention. So, if you remember, I told you easy direction you retain a lot, in the hard direction you retain little magnetization. Okay. So, again that also you can understand by this analogy. let us say you drive a car from here to here, say at this point you apply brake, okay, remove the brake, your car will be still here. Okay. Same thing. So, in this case the easy direction, let us say you drive your car from here and you apply brake, remove your brake, okay, your car will be still here. Okay. So, car will be left where you left it. On the other hand, let us say you try to drive along this one, this direction, you apply brake, remove the brake, what will happen? Yeah, the car will come back, it will not stay here, it will come back. So, this is another property of the hard direction. So, this is equivalent to retention of magnetic moment. So, here I am talking about retention of car in its initial position, but in magnetism we are talking about retention of magnetization. So, in the case of easy direction, you apply magnetic field, you have certain magnetization, and if you remove the magnetic field, you are almost there. Okay. So, you retain much of the magnetization. So, this is a property of easy direction. In the hard direction, you will almost retain nothing or a little bit. Okay. So, depending on the property of the material that you make, in the hard direction you will basically retain much less. Okay. So, that also explain what I have drawn here. So, you can see in the easy direction we have retained much of the magnetization, in the hard direction we retained less. Okay. So, these are the important properties of anisotropy. Okay. So, if you measure properties of a sample in the easy direction and a hard direction, you will find these differences. For example, in the easy direction you need very small field to raise the magnetization value very quickly. Okay. Here you see you need much larger field to go to that same level. Okay. Somewhere here you need much larger field compared to here. And you can also notice that once you remove the magnetic field, so you know that here is 0 field, right. So, 0 field, a large magnetization is retained, whereas here the retention is almost 0. Okay. So, this will be the difference between the hysteresis loop in the easy direction and the hard direction. Okay. So, we learnt about what is anisotropy. Anisotropy is the property of magnetic material being different based on the directions in which you measure magnetic property. In the case of the car analogy that I gave, the anisotropy came because of the topography. So, in one case you have a flat road, in another case you have a road with some curvature. So, the topography gave rise to the anisotropy. In the case of magnetic materials, this magnetic anisotropy can come from various sources. So, it can come from the crystallographic nature of the sample. So, when the anisotropy comes from the crystallographic nature of the sample, we call it magnetocrystalline anisotropy. And if it comes because of the shape of the material, then we call it shape anisotropy. Okay, let's say you keep two different materials together. Let us say this one piece of material, this another type of material. You put them together, then there is an interface between these two materials. And if the anisotropy comes because of the interface between two different materials, then we call it interface anisotropy. And let us say you bend or stretch some film, you cause stress in the material, and if the anisotropy comes from the stress, then we call it stress anisotropy. And sometimes let us say you deposit a magnetic film. During the magnetic film deposition, you apply a certain magnetic field during the deposition, and the magnetic field can induce certain anisotropy in the film. So, that is called induced anisotropy. Okay. So, there are various types of anisotropy. The origin for magnetic anisotropy can be coming from various factors. Okay, let us first discuss magnetocrystalline anisotropy. So, as the name implies, this anisotropy comes from the crystalline property of material. Okay, so, whether we are going to study magnetic recording or magnetic random access memory, we will be dealing with cobalt often. Okay. So, in the case of cobalt, you have a hexagonal crystal structure. So, in this picture all these dots represent cobalt atoms. So, if you take a unit cell of cobalt, the cobalt atoms are arranged in hexagonal crystal structure. Okay. So, this is a hexagonal crystal structure. So, in the case of cobalt in a hexagonal crystal structure, this direction is the easy direction. Okay. So, traditionally we call this as A direction, and this is also A direction, and this direction is called C. Okay. So, the easy direction is along the C direction. So, what it means is that if you do not do anything special at ground state, the magnetic moment of all these cobalt atoms are pointing along this direction. Okay. So, when the magnetic field is 0, I mean in the ground state, all the magnetization is pointing along this direction. So, when you have a bulk cobalt, okay, you have a single crystal cobalt, then you apply a magnetic field along this direction. Okay. Let us say now we apply magnetic field along this direction and measure the magnetic property of cobalt along this direction 0 0 0 1. Then you notice that the magnetization rises rapidly. Okay. So, within a very small field, you can see that it jumps to a very large value. Okay. So, I told you that in the ground state you do not do anything, they are already along this direction, but this sample, this is an experimental result, right. So, experimental results in this sample may be some of the cobalt atoms are not in this direction, there may be some difference in the sample condition imperfections. So, because of that you need certain magnetic field to reach the saturation value. Otherwise, I mean theoretically, if you do not apply any magnetic field also, all these magnetization are already pointing in this direction, you will need almost 0 field to reach this saturation. Okay. But this is an experimental result. So, there may be some imperfections, and because of that you need certain magnetic field to reach the saturation. Okay. So, you can see that this is the easy direction, means very small magnetic field you can reach high magnetization values. Okay. Now, let us try to apply magnetic field along the hard direction. So, you can say this is a hard direction, this is a hard direction. Okay. So, let us say this bottle represents the cobalt crystal. Okay, this bottle represents cobalt crystal, and c axis, easy axis is along this direction, the height direction. C axis is along this direction. So, in this direction, if you apply magnetic field, you can saturate easily. Now, let us say we apply magnetic field along this direction. So, one of the radius direction of the bottle. So, our field is either along this direction or towards you, does not matter. So, we are applying magnetic field along the hard direction 1 0 1 0. Then you notice that the magnetization does not increase sharply, it increases almost linearly, slowly. Okay, then finally, at a very large magnetic field, it becomes comparable to the magnetization in the easy direction. So, what happens during this time is that, I mean, at the 0 field, all the magnetization is pointing up. Then as you increase the magnetic field, so let us say this is the original direction of magnetic moment of one cobalt atom. So, as you increase magnetic field, this is slowly coming to this direction, and for after very large magnetic field, the magnetic moment of cobalt turns towards this direction. Okay, so, it rotates slowly from this direction towards your applied field direction. Let us say I reach here. Now, all the magnetic moments are pointing in this direction. Then I suddenly remove the magnetic field. What will happen? Yeah, so they will come back. So, suppose I reach 10,000, I suddenly remove the magnetic field, come back to 0, then all these magnetic moments will come back to the ground state. Okay. So, once I remove the magnetic field, it will come back here. Whereas, in the case of the easy direction, let us say I apply magnetic field here, I remove, they will be somewhere here. Okay. They will all be pointing in the direction. Okay. So, this is magnetocrystalline anisotropy, and here this anisotropy is coming from the crystallographic structure. Okay. So, this is a explanation of what I showed you so far. So, I apply a magnetic field. So, initially the let us go back to the other one. So, I apply certain magnetic field in the opposite direction. Once that value exceeds certain field, you can see that all the magnetic moments flipped, but once I remove the magnetic field, the magnetic moment is still retained in the same direction. Okay, because there are two easy directions, either magnetization pointing in this direction or the other direction, both are easy directions. Okay. Now, if you apply magnetic field in the hard direction, as I increase, you can see that the spins rotate along the field direction, and if I reduce the magnetic field, they all go back to the ground state. Okay. Okay, so that is one type of anisotropy. The second type of anisotropy comes from the shape of the sample. Okay. So, let us say you have a bottle, you have a paper. So, you can see that the bottle and paper have different shapes. Okay. So, if you prepare some magnetic materials in a cylindrical shape or in the form of thin film, then you will have an anisotropy that comes because of the shape. Okay. So, the shape anisotropy is usually dominant in the absence of a strong okay. So, let us say there is no other form of anisotropy. Okay. So, there is no magnetocrystalline anisotropy. Okay. Then you prepare certain material into a cylindrical shape or the shape of a paper. Then because of the shape there will be some easy direction and hard direction, and that is called shape anisotropy. Okay. How many of you have seen the horseshoe magnets? Have you seen these magnets? Okay. So, usually these magnets are popular long ago, maybe hundreds of years ago, when people did not have materials with a high anisotropy. Okay. So, at this point of time, I mean when people made this kind of horseshoe magnets, the materials used for these magnets themselves have low anisotropy. Okay. So, they did not have a strong magnetocrystalline anisotropy. Okay, and they use this shape to create some anisotropy. Okay. So, the horseshoe magnet is one example of a magnet that uses shape anisotropy. Okay, so, to understand shape anisotropy, let us follow this rule of thumb. Okay. So, for example, let us say I have this a magnet which looks like this bottle. I magnetize along this direction. So, let us say we have a north pole here and south pole here. Okay. So, when I magnetize this magnet along this direction, you can see the north pole is here, south pole is here, and they are separated by about 20 centimeter. Okay. Now, I take the same piece of magnet, I try to magnetize along this direction, the radius direction. So, let us say I have north pole here, south pole here, they are separated by around say 6 centimeter. Okay. So, the shape anisotropy prefers that the north and south poles must be far from each other. Okay. So, we magnetize this in two direction. In one case we magnetize along this direction, in another case we magnetize along this direction. So, here you see the spacing is 20 centimeter, here the spacing is 6 centimeter. Okay. So, shape anisotropy dictates that this will be the easy direction, okay, because in this direction if you magnetize, the north and south poles are far away, whereas in this direction the north and south poles are not far, only 6 centimeter. So, this will be the easy direction, this will be hard direction. Okay, now, I have a magnet looks like this. So, here which is the hard direction? Yeah. So, this will be the hard direction, because if you magnetize along this direction, your north pole and south pole are like 5 millimeter away. On the other hand, if you magnetize along this direction, maybe it is like 30 centimeter, this direction around 20 centimeter. So, this will be the easiest direction, easiest direction is along this. This is a bit hard direction and this is the hardest direction. Okay. So, in a sheet of paper, hard direction is perpendicular to the plane of the paper, and if you take a long wire, the easy direction is along the length of the wire. So, if you take an ellipse for example, so if you north and south poles are far away, so this is the easy direction. If you magnetize along this direction, north and south are closer, so this is hard direction. Okay, so this is the concept of shape anisotropy.
Sir, what a horseshoe magnet? How will we?
Horseshoe magnet is like your, this is the length, right. So, the easy direction is along this length. So, it is like a long wire. So, it is like this. So, it is like a long wire. So, easy direction is along this length and you just bend it. Yeah. In a single crystal and polycrystalline sample, how will the direction of field depend? I mean, in a single crystal, you can mark, like, let us say you buy a single crystal sample and it comes with a marking. Let us say they will have, this is one particular direction, and let us say this is the easy direction. You can easily measure the hysteresis loop along the marked direction and say 90 degree away from that. Okay. So, in single crystal it is easy to do, you know where is the easy direction, which is the hard direction, but in polycrystalline materials you do not know exactly, okay, because you may have texture or you may not have texture. Okay. Let me come back to this one. Okay, one example of a polycrystalline material. Anyway, to go to the white screen from here. Okay, let me draw something here. The hard disk media, the magnetic films that store information in the hard disk drive, they are a good examples of polycrystalline systems. Okay, so, in this system we have tiny crystals separated from each other, and in the recent hard disk drives. So, these grains have magnetic anisotropy in the perpendicular direction. So, their magnetization may either point into the board or the magnetization may be point away from the board, and these are usually highly textured films. So, when I say textured films, we prepare the easy direction of these grains. So, now I am looking at the cross sectional point of view. Their easy direction may be mostly pointing in the perpendicular direction, whereas some grains may have slight tilting. Okay, so, this property you will see in polycrystalline materials, but in single crystalline material almost all the grains will be pointing in the same direction. Okay, so, because of that you will see difference in the hysteresis loops. So, in one case, for example, when you measure a single crystal film, you may have like very clear idea of easy direction and hard direction. But in the case of polycrystalline materials, you have like there is some variation in the easy direction. So, your hysteresis loop will be a mix of property from different grains. Okay. I do not know whether I answered your question, but you will see differences in the measurement. Okay. What is the next question?
Also, if we measure resistivity in presence of
Mhm.
Will the resistivity be affected by the applying different field if the material shows the polar phenomenon?
Yeah. So, we will be discussing this property where the resistance depends on the magnetic field in a later section. So, we will discuss that then.
The last question, the animation source for the field removal in the single crystal of cobalt
Mhm.
was for a perfect crystal without defects.
Mm-hmm.
Therefore, the magnetization traced back initial path with zero remnants, right?
Animation for shown for field reversal in single case. In the hard direction, yes, the remnants will be 0. Yes. So, I think this question is referring to the video I showed for hard direction. So, that's anyway animation. So, I am just explaining what is happening in the cobalt unit cell level. Yes. So, yeah, you are right. Any other question? Okay, if not, let us move on. Okay, so, the shape anisotropy comes from this property called demagnetizing field. Okay. So, to understand this concept, I need to introduce a few more terms. Okay. So far, I introduced magnetization, I introduced a magnetic field, applied magnetic field, but a few other things I have introduced. Okay. Let us say you have a piece of magnetic material, you apply certain magnetic field, then you can orient the magnetic moments of this particular material along certain direction. So, we can say the magnetization of this material is pointing along this direction. Okay. So, this is magnetization, and this magnet itself will produce a magnetic field. Okay. So, this magnetic field will be like this, shown by the blue arrows outside the magnet. Okay. Outside the magnet, I mean, by convention we always say that the magnetic field goes from north pole to the south pole. Okay. So, outside the magnetic field will go along this line. Inside the magnetic field will go this way, again north to south through the material. So, if I have a magnet like this, so there is a field inside this material that goes from this side to the outside through the, let us say, through the center of this bottle. Okay. So, this field is called demagnetizing field. Okay. Then you also know that by Maxwell's law, the B is always forming a loop. So, the B inside B is magnetics induction. Okay. So, it follows this pattern. Okay. So, the B, H and M of a magnet will have this kind of properties. Okay. Now, you see that there is a magnetization which is pointing along this direction, and inside there is a magnetic field that is opposite to the magnetization. Okay. So, you can notice that this H is opposite to M. Okay. So, this H will always tend to destabilize M. If H is large, then M is not stable along that direction. Okay. So, this is the reason we have the rule of thumb that I stated before. So, north and south poles must be far away from each other. Okay. So, if north and south poles are far away from each other, this field will be small. Okay. This is called a demagnetizing field. It is d small when north and south poles are far away. Let us say I magnetize this magnet along this direction, then my demagnetizing field is along this direction. Now, north and south pole are nearer. So, this field will be stronger Okay. So, it will not favor this direction. Okay. So, this is the origin for shape anisotropy. The demagnetizing field gets larger in certain direction. So, that you can understand by looking at these tensors. Okay. So, in certain direction the demagnetization field will be larger, and that will oppose magnetization to be in that direction. Okay, that is about shape anisotropy. Okay. So, here I am showing different example. So, if you take a piece of paper like this, then when you try to apply magnetic field along this direction, since the demagnetizing field is very large along this direction, magnetization usually do not stay in the perpendicular direction. And like, let us say, I mean this example is very useful when you look at thin films. When you prepare thin films without any special anisotropy, so if your thin film have no special anisotropy, then the magnetization will never be along this direction. Okay. The demag field is very strong along this direction. So, when there is no special anisotropy, the magnetization of thin film is always parallel to the film, either along this direction or this direction. Okay. So, in the case of thin films with no anisotropy, the magnetization will be either parallel along this direction or this direction. Okay. So, when you have a magnet of this shape, again when you talk about this direction, the north and south pole are very far. So, H d is negligible, but if you talk about this direction, H d is high. So, the magnetization is not favored along this direction. Yeah. So, here is a weak demagnetic field. If magnetization is along this direction, demag field is weak, but if magnetization is along this direction, there is a strong demagnetizing field. This is for this case. Okay. So, this is the concept of shape anisotropy. Any questions so far? Okay, now we move to the third one, interface anisotropy. So, I told you, like for example, if you make a thin film of cobalt, as such the thin film does not have much anisotropy, and because of that the magnetization is always going to be parallel to the film plane. Let us say this is a substrate, on top of this we are depositing a cobalt film. So, the magnetization will lie parallel to the plane of the film, the substrate. So, this is the normal case. On the other hand, let us say you prepare a multi-layer of cobalt and platinum. For example, this layer, the green layer is cobalt, white layer is platinum. Okay, so, you do cobalt, platinum, and so on. So, you stack many layers of cobalt and platinum one top of another for certain thickness, very low thickness. For example, let us say this cobalt is only like 0.3, 0.4 nanometer, and this platinum is like say 0.8 nanometer or so. So, when you deposit very thin layers of cobalt and platinum, stacking one top of another. So, people have found out that this film can have perpendicular anisotropy. Okay. So, here you have lots of interfaces of cobalt and platinum. So, here your cobalt is cobalt throughout. Okay. So, the cobalt atom here, cis neighbor also is cobalt, bottom neighbor, top neighbor, all are cobalt for this particular case, whereas in this case a cobalt here will see platinum as a neighbor in the top surface and so on. Okay. So, you are modifying the interface, and because of this interface there is a perpendicular magnetic anisotropy. Okay. So, now here this is the easy direction. Now, you see that the easy direction is pointing perpendicular to the film plane. So, somewhere in 1980s people found out that when you deposit multi layers of cobalt and platinum for certain thickness, you can have the magnetization in the perpendicular direction, and this type of anisotropy is called interface anisotropy, okay, because you are creating interfaces. Okay, so, you have cobalt interfaced with platinum, platinum interfaced with cobalt and so on, and that is why you are getting this anisotropy. Okay, so, this is one example of interface anisotropy. You can interface a ferromagnetic material with the antiferromagnetic material. So, this is another type of interface. Then you can get another type of anisotropy. You can interface soft magnetic material with hard magnetic material, or you can, I mean, like I described now just now. Here we are interfacing magnetic material with a non-magnetic material, and we get perpendicular anisotropy. Okay. So, these are some examples of interface anisotropy. Okay, so, now let me explain this one, the ferro antiferromagnetic interface. Let us say you have a ferromagnetic film in proximity with an antiferromagnetic film, and this is the interface. Okay, you do some process. Okay, there is some recipe which I will give you another time. There is some recipe you need to follow, and you make this kind of film. Okay, after doing this recipe, you have the spin structures as shown in this picture. Okay. So, the antiferromagnetic spins, you can see that they are antiparallel, okay. But at the interface you can see that these spins of the antiferromagnetic material and the ferromagnetic material are parallel. So, you have formed this kind of interface, and now if you measure the hysteresis loop of this ferromagnetic film, I mean you are measuring the hysteresis loop of this whole thing, but antiferromagnetic material will not show anything significant, because you know that their net magnetization is 0. So, what you will see is the magnetization response of the ferromagnetic film affected by this antiferromagnetic film. Okay. So, you will get a hysteresis loop which looks like this. So, this is the hysteresis loop of antiferromagnetic ferromagnetic interface. Okay, so far I have drawn many hysteresis loops, right, and here you see another hysteresis loop. Do you see any difference? Yes. Okay. You see that the hysteresis loop is shifted. So, whenever I was drawing hysteresis loop, that is symmetric with respect to the magnetic field. Okay. So far all my discussions I showed you hysteresis loop which was symmetric with respect to the 0 axis of magnetic field, but here you see that the hysteresis loop is shifted. So, this is the center of the hysteresis loop, and this is the H is equal to 0 axis. Okay, so, this is negative H, this is positive H, 0 is here. Okay. So, you see that the center of the hysteresis loop has shifted by certain field. Okay. So, this field people use different terms. So, some people use it HEX or HEB. Okay, let us use this term EB, HEB, where EB stands for exchange bias. Bias means what? Bias, you know, right? You are not in the center, you are not taking neutral decision, you are biased to one side. Okay. So, in this case the hysteresis loop is biased to one side. Okay. So, the center of the hysteresis loop is on one side of the field direction. Okay. So, it is not here, you see it is unbiased. The hysteresis loop is symmetric with respect to 0 field, but here the hysteresis loop is shifted towards one direction, it favors this direction, it is biased toward this direction. Okay. So, this field is called exchange bias. What is the condition to get this? I told you that there is some recipe which we will discuss later. So, time being you assume that you have done something and you have this, and you are measuring the magnetic properties, then you see this one. Yeah, possible. Okay. So, I asked you the question, what difference you see? I got one answer, which is the shift. Okay, that is correct. But is that the only difference you see? What is that? Huh?
The width of the hysteresis curve is of transition from the remnants to this.
Remnants, what is? Positive. Okay. I mean, what other difference you see between this loop and this loop? Huh? Rectangle. Okay, that depends on how. I cannot draw a perfect rectangle. Okay, so my rectangle is like this. That is not the MR is equal to. That also you can assume that I draw badly, and that is why MR is not same as MS.
The shift can be along the direction.
Pardon?
The shift can be along the
Y direction, no. I mean, we are not talking about that. A very clear difference you should be able to see. What did you say about remnants? Straight line to? You are talking about this sharpness. No, that is not the case. That one depends on how well I can draw. I can draw exactly the same thing. So, let us say I draw, I am not very good, but let us say I can draw. That is not the case.
Also, only providing field in one direction, not on the opposite direction, like only.
No, I let us say assume that I am going from here all the way here. That is not the difference. A very important difference you should be able to see.
non-zero magnetization at the not applied field at zero applied field.
Non-zero magnetization.
When no external field is applied,
Mm-hmm.
H0
Mm-hmm.
only in the negative direction.
Yeah. Okay. That is the important point. Okay. So, let me erase this. So, in the normal hysteresis loop which I draw every time, how many remnant states exist? 2, right. So, if you apply magnetic field along this direction, let us say magnetization pointing up and here magnetic field is like this, magnetization pointing down. So, you have two remnant states depending on, let us say you saturate along this direction, when you remove magnetic field your magnetization is pointing in the up direction. If you apply magnetic field in the down direction, you remove, your magnetization is pointing in the down direction. Okay. That means, if you have a magnet, so you may have north pole here, south pole here, or south pole here, north pole here, depending on which field you apply. Okay. But in this case, you see, let us say I start from here, I can go all the way, come back, go back. So, I have one remnant state. If I do the same thing, let us say again I start from here, I apply, go all the way, come back, I will end up in the same state. Okay. That means, if I have something like this, my north pole is always going to be like this. Whatever I do, I apply magnetic field, very large magnetic field along this direction. If I remove, still my north pole is going to be the same. I can never make this to be a south pole. Okay. So, let us say here this particular film has only one remnant magnetization direction. Whether you apply negative field or positive field, you will always end up with this configuration. You will never have this configuration. Okay. So, this is the property that we can get with exchange bias, and this anisotropy is also called unidirectional anisotropy. Okay. So, as I mentioned before, previously you have two directions. So, you can have this magnet to have north pole up or south pole up, depending on which direction of magnetic field you apply. On the other hand, in this configuration, my magnet will have only north pole up, irrespective of my field treatment. Okay. So, there is only one direction, magnetization will be only one direction, magnetization at remnants. Okay. Remember this one. So, at 0 field, the magnetization has only one direction. So, this anisotropy is also called unidirectional anisotropy, and it arises from the interface between the antiferromagnetic material and the ferromagnetic material. Okay, we will do a few questions, then take a break. It's same as yesterday. So, if you had already opened the tab, you can use the same one. This one we have done before. Okay, we will do this. Oh, what is showing?
It's showing some code.
Some. Okay, this is a different code, is it? Yeah, same code, the one you used yesterday. So, I will give you more time for this question. So, in your browser type voclap.com, and when it asks for code, you type spin week 2. Okay, most of you are right. The correct answer is hard magnetic materials are difficult to demagnetize. Next one. Okay. Majority of you are wrong. Okay. Why wrong? I cannot write here. Okay. Okay, majority of you are wrong because all of the above means this is right, but this is wrong. Okay. If you take a material, okay, let us say this material, whether you are, let us assume you are comparing between this direction and any axis within the plane. Okay. So, in the when you apply magnetic field in the plane of that paper, you will reach saturation quickly and you will have a hysteresis loop like this. Okay. Now, I apply magnetic field in the perpendicular direction. I need more magnetic field. Okay, my hysteresis loop may be something like this, okay, in the hard direction. Okay. So, at a large field what happens? At this field the MS is the same. Okay. So, whether you apply magnetic field in the easy direction or hard direction, MS is the same. Okay, by definition, your magnetization is the sum of magnetic moments of all the atoms divided by volume, right. So, inside that material volume did not change, MA did not change. Okay. What has changed is only like the field you need to make all the magnetization to point in one particular direction. Okay. So, at very large field, the hard direction also will have the same saturation magnetization. Okay. So, because you thought this is correct, so many of you chose this one. So, this is the correct answer. I am also wrong. Correct answer is 2. Okay. Next one. Okay, I do not know why still some of you are answering wrongly. This should be a very simple question. So, the correct answer is direction A. Okay, so we have some more questions pending. I think time to go for break. Yeah. So, we will have tea break now, then come back after 15 minutes.
on the mic. So
Yeah, I am not talking now, just I am drawing. Okay, so during the break there was a question whether the MR of the polycrystalline films, how close they can come towards MS, okay, in polycrystalline films. So, I have seen this growth, I mean the improvement in making MR as close to MS in possible. This has happened in magnetic recording technology. So, initially the magnetic recording technology was based on magnetization parallel to the disc surface. So, that is called longitudinal magnetic recording technology. So, in the early days we are using small grains to store information. So, whenever I show one arrow, basically that arrow is the magnetization direction of one particular grain. So, it may be like this or in any other angle, but it is basically one grain. So, we store information in many small grains. Okay, so, if you look at the technology of longitudinal magnetic recording in the 1990s, for example, we can view the EZ direction in two different perspectives for the longitudinal sample. Okay. For example, let us say let us say you are storing in magnetization along this direction parallel to this surface. You can view the easy direction from this angle. Okay, you are viewing the easy direction from this angle, or you are viewing the easy direction from this angle. Okay. So, I am showing the two perspective. So, in longitudinal magnetic recording, your grains may have easy direction. I mean, if you view from this perspective, it may be completely parallel to this plane, or it may be tilted at some angle with respect to this plane. So, magnetization can be this way or like this, okay. A few possibilities exist. And now, if you view from the top, so within the plane, again the magnetization can point towards you or point towards this wall or point towards this wall. So, it can point towards many directions, right. So, from the top also you have randomness. So, when you have such randomness, usually the MR is very low compared to MS. So, you may get something like 0.6 times MS. Okay. So, this value is 60% of the MS value. So, people have improved this randomness by using some growing some underlayer and things like that. So, for example, they can minimize the randomness of the easy axis away from the parallel direction. So, you see the randomness is more here, is reduced. So, more easy direction is parallel to the disk surface, but still within this plane there is randomness. Okay. So, in this case you can see the MR approaches around 0.7 times MS. Now, let us go further. You make all these grains to have easy direction parallel to the disk surface, and again this also you minimize. So, instead of this magnetization pointing in different direction, I try to force most of the easy direction along this. Okay. So, when I do that, I can go to around 0.8 times MS. That means, this value is 80% of the MS. Okay. So, this kind of improvement can happen. Then somewhere in 2006, hard disk industry switched to perpendicular recording technology. Now, the magnetization is not in the plane, now magnetization is perpendicular to the plane. So, when you have perpendicular to the plane, I mean in this direction you do not have much variation, like you see right here within the plane I can have random orientation, but when you orient all the magnetization along the perpendicular direction, there is no in plane variation. So, now you have only variation in the easy direction with respect to the film normal. So, some grains may have easy direction perfectly perpendicular, some may have easy axis tilted along this direction or this direction. So, when you go from longitudinal to perpendicular, you can roughly achieve 90% of saturation magnetization. And now, if you try to minimize this randomness, you try to make all the grains having easy axis perpendicular, then you can bring the MR very close to the MS. So, even with polycrystalline materials, you can improve the process to ensure that your film is textured. So, we call this textured. You try to make all the easy axis along the same direction, then you can achieve high values of MR over MS. Okay, so far we have answered the first two questions. The next question is like, for For example, yesterday we were discussing about Curie temperature. I asked you a question, if you heat a magnetic material above Curie temperature, then you bring it back to room temperature, whether the ferromagnetic material will be same as ferromagnetic material. You all answered yes, and that is correct. So, my next question was like, in your school you would have learned that if you have a permanent magnet, do not heat it. If you heat it, your permanent magnet will lose its property, right. It is ferromagnetic material, but it loses the north south poles. Okay. So, a permanent magnet has a fixed north and south pole, but if you heat it and cool down, it will lose its north and south poles. It will not attract any magnetic material. So, what happens? What is the reason? And that is what we are going to learn now. And also we are, okay, let us say I have neodymium iron boron in my lab. Say I do some mixing and do all the processes to make it a neodymium iron boron magnet. Okay. So, I did all the chemical steps necessary to make this compound. Okay. I have made this compound, and this compound is in this shape, for example. Okay. But when I do this, this is not a magnet on its own. Okay. So, this piece of neodymium iron boron does not have a fixed north pole or south pole. So, I need to do one additional step to make this a permanent magnet. Okay. So, what I need to do is, I need to subject this particular piece of magnet to a very strong magnetic field. So, typically this is like a 3 Tesla kind of field. So, I apply very large magnetic field, then I force all the magnetization to point along this direction. Then once I remove the magnetic field, now I still have a north and south pole. Okay. So, this step is important. So, you need to apply a very strong magnetic field, only then you can create a north pole and south pole and make it a permanent magnet. So, what happens when you prepare a piece of neodymium iron boron piece? Okay. So, in this piece you notice that there are tiny regions where magnetization are pointing in different direction. Okay. So, because the magnetization is pointing in different direction, you do not have a north pole or south pole, but once you apply a very strong magnetic field and even after you remove, the magnetization is retained in this direction, then you have a north pole and the south pole. So, now you have a permanent magnet. So, why does a freshly prepared piece of neodymium iron boron magnet have magnetization in random direction? What causes this randomness in the magnetization direction of this material? And that is what we are going to learn now. Okay. So, that brings us to this concept of magnetic domains. So, when you prepare a fresh piece of magnetic material, not all the magnetization is pointing in the same direction, but you will see some regions where the magnetization is pointing in one direction. So, if I zoom in this particular region, I will notice that the magnetization of the neighboring atoms are pointing in the same direction. So, if I zoom this one, the magnetization are pointing in the same direction within this microscopic region. Okay, so, within this microscopic region, the neighboring atoms have parallel magnetization, which means it is ferromagnetic. But on a whole, the system divides into many small regions with random magnetization direction. Okay. So, this property is called magnetic domains. Okay. So, domains are the tiny regions in a magnet, where within a domain the neighboring moments are parallel to each other, but within the bulk of a material you have the system pointing magnetization in different direction. So, this concept is called domain. So, you can call each of these region as a domain. So, this is a magnetic domain, this is a magnetic domain, this is a magnetic domain, and so on. Okay. So, there are many magnetic domains inside a magnetic material, especially when you have not subjected a magnetic material into a magnetized state. So, freshly prepared material like the neodymium iron boron, which I prepared, has many domains. Okay. So, what causes these magnetic domains? Again, let me go back to, let me create a fresh page. Yeah, create a new slide. Yeah, I can use the 104. No, yeah, I can use that. No, it's okay. If 104 is fresh, that's fine. Okay, so let me ask you a hypothetical question. Let us say I have two magnets, the two magnets, both of them have north pole up. I try to bring them close to each other, what will happen? They will repel. Okay. What else can happen? I try to bring too close and I am not holding it tight. They can rotate, right? They can rotate and probably they will form so why this happens? Pardon? Yeah, so it's a energy minimization. Okay. So here when you have two north poles, two south poles next to each other, the energy is high. This one is state of low energy. What is the name for this energy? So, this energy is called the magnetostatic energy. Okay. So, magnetostatic energy is minimum when you have two unlike poles next to each other. Okay. And when you have two like poles next to each other, the magnetostatic energy is high. So, when you bring two magnets, they flip into this direction to minimize the energy. Okay, let us say I try to prepare a piece of neodymium iron boron. Okay, I have formed powders. So, I bring all the powders close to each other. So, each tiny piece of iron has certain magnetic moment. Okay. So, these are the atomic moments of the neighboring ion atoms. So, let us say I keep doing this along the 3 dimension. So, what happens? So, when you look at this one, this is like trying to keep 2 north poles next to each other, 2 south poles next to each other, right. So, I cannot keep piling the neighboring atoms to be parallel to each other, because when I keep doing that, I am increasing the magnetostatic energy of the system. Okay. So, the system will tend to minimize the energy. Then only way to minimize the energy is to bring some randomness or to form this kind of pattern. Okay. So, if they flip, for example, in the case of real magnets, they can flip and form this to minimize energy. So, in the case of a system like this, again they can flip, for example. In some cases we have this kind of flip. So, now you have one domain, then we have another domain and so on. Okay. So, formation of domain helps to minimize magnetostatic energy. Okay. So, here I draw 2 domains with some space intentionally. Why? Why didn't I draw like this? Yeah. But why I didn't draw? Pardon? Yeah, why? So, why I kept some distance here? Pardon? Some boundary is there. Yeah. Why that boundary happens? Pardon? Yeah, but why the boundary cannot be sharp?
So, abrupt boundary cost high energy.
Yeah. Okay. Due to some concept that we learned earlier. What is that? Yeah. So, okay. So, we learned that the Heisenberg interaction states that the neighboring spins have to be parallel. Okay. So, this is S1, S2 cos theta, theta has to be 0, right. So, if you go from 0 to 180 abruptly, then the energy is going to be very high. Okay. So, because of that reason, the spins do not change abruptly from one direction to the other direction, but they will change gradually like this. Okay. So, this boundary or this region where this transition happens is called a domain wall. So, we have 2 domains and we have a domain wall in between, and the domain wall ensures that we do not violate this. Okay. We do not increase this energy drastically. Okay. So, when you go slowly from 0 degree to some angle gradually, so the angle between these 2 spins will be for example, let us say this is like 15 degree, this is another 15 degree and so on. Okay. So, the angle theta never goes from 0 to 180 degree, but it may go from 0 to 10 degree or 15 degree depending on something that we will learn later. Okay. Okay, so here I am just visually showing whatever we discussed. So, when we try to put many atoms with spin pointing in the same direction, we are increasing the magnetostatic energy, and on the other hand, if the system forms domains, then the magnetostatic energy is minimized. Okay. So, I try to put many neodymium iron boron atoms together. So, magnetostatic energy gets increased, but the system forms many domains and minimizes the magnetostatic energy. Okay, so, this picture shows what we discussed earlier. So, we have one domain where all the spins are up, we have another domain, all the spins are down. So, in between we have a gradual change of magnetization from up to down direction, and this is called domain wall. So, there are, I mean, in perpendicular system there are like two different types of walls. One is called Neal wall, another is called block wall. So, in Neal wall, the let us say this is up spin, then this region has down spin, the magnetization goes this way. Okay. So, if you look at the, how do you remember? So, quite, I mean, when I was young, I always have difficulty to remember which one is Neal wall, which one is block wall. In the case of block wall, the magnetization goes this way, it comes towards you, then comes back down like this. Okay. Whereas, in the case of Neal wall, it just goes this way and this. Okay. So, I always had difficulty in remembering, then I came up with the mnemonics. Okay. So, when you kneel down, what you do? You are bending something like this, right. So, if you look at this one, you can see that this pen is actually kneeling down. Okay. So, remember this mnemonics to remember how the Neal wall looks like. Okay. So, these are two types of domain wall in perpendicular systems. Okay. The next question is whether a system will always form domains or not. Okay. So, I gave you the example of a neodymium and boron magnet, and I told you that here we will form domains. Okay. There are also some systems where we may not form domains. Okay. Especially when I talk about recording media, the hard disk recording media. We do not form domains, no domains. So, when I prepare a recording media film, that film does not form domain. Okay. This might look surprising to you, because if you have studied about domain, you would always think that all systems will form domains, but that is not the case. Okay. There are some cases where the systems may not form domains. Okay. So, what determines whether the systems will form domain or they will not form domain depends on the competition between two energies. Okay. So, to explain the two energies, let me go back to the white screen. So, when you form a domain wall, or when the system forms domains and domain walls, the system reduces magnetostatic energy okay. So, this we have already learnt. Okay. So, it is like having a magnet flipped and attracted to each other. So, this we already learnt, but the formation of domain wall actually increases something called domain wall energy. This we have learnt. Okay, I haven't taught you what is domain wall energy, where does it come from. Okay, so, this domain wall energy comes from two aspects. One is the anisotropy, so anisotropy energy. The other contribution is coming from exchange energy. Okay, so, when you form a domain wall, there is an energy associated with formation of domain wall. Okay. So, there is an increase in the energy of the system. So, the more domain walls, then more energy. Okay. So, as you add more and more domain walls, the system's energy also increases. Okay. So, this domain wall energy comes from two factors, one is exchange energy, another is anisotropy energy. So, what is this exchange energy? Where does it come from? Okay, let us go back to the domain wall. So, let us say we have spins like this, here we have spins like this. So, within the domain wall we learned that the spins have certain angle. Okay. So, if you look at these two spins, theta is 0, Heisenberg exchange energy is the lowest, but if you look at these two spins, theta is non-zero. Okay. Even though the spins are at certain angle, this tilt actually increases the exchange energy. Okay. So, all these spins at the domain wall, they are not at theta 0 angle, they are at non-zero angle. Okay. So, because of this there is a energy. So, that energy is called exchange energy, increase in exchange energy. Okay. Secondly, where does this come from? Anisotropy energy. Let us say this is a perpendicular film, okay, a film with a perpendicular anisotropy. So, let us say this is your substrate and this is the film you prepared, it has a easy direction in the perpendicular direction. Okay, so, we know that the energy is minimum when the spins are pointing in the easy direction. So, if the spins are pointing away from the easy direction, then there is going to be some energy. So, you look at all these spins. So, these are okay, these are in the easy direction. So, there is no energy contribution from these spins, but all the spins in the domain wall region, they are not in the easy direction. So, this is deviated from the easy direction by certain angle, this is deviated even more further. So, this increases energy a little bit, this increases energy too much, and this increases the energy the most, and so on. Okay. So, because the spins are not aligned along the easy direction, the anisotropy energy also increases. So, when you form domain wall, when you form many domains, the domain walls also need some energy, increase the energy. Okay. So, exchange energy increases, anisotropy energy increases. Okay, so you can see that two cases, one is domain wall formation reduces magnetic energy, but domain wall formation increases the domain wall energy. Okay. So, finally, whether the system will form domains or not depends on the competition between these two. Okay. Suppose you have a system, and in that system if the formation of domains reduces the magnetostatic energy drastically compared to this one, then the system will form domains. Okay, suppose by forming domains you will increase the domain wall energy more than the reduction that you can gain from here, then the system will not form domains. Okay. So, that is what is shown in this picture. So, here I am plotting the energy, the energy from magnetostatic energy is given by this red line. It goes as L power 3, whereas the formation of domain wall has a L square dependence. Okay, so here you can imagine a cube, for example. Okay. So, if this L is very large, okay, then we are in this region. Okay, for large L, you are in this region. So, that means the magnetostatic energy is much larger than the domain wall energy. So, here we will have formation of domains. On the other hand, if the L is small, below a certain critical size, now the domain wall energy is more than the magnetostatic energy. Okay. So, in this case no domains will be formed. Okay, I hope it is clear. Any doubts here? Is it easy to understand or difficult? Okay, let me show you some more slide. Okay, let us say you prepare particles. Okay, let us say you do some chemical process and you prepare nanoparticles. Okay, so, these nanoparticles have certain diameter. So, if these particles are very huge, okay, if these particles are very huge, so particle diameter is large, then you are in this region where magnetostatic energy will be is more than the energy needed to form domains and domain walls. Okay. So, in that case this particle will not have single domain, it will have many domains. Okay. So, it will form multi domains. So, in your chemical synthesis you have lots of such particles all the particles are above certain critical dimension. So, magnetostatic energy is more than the domain wall energy. So, all these tiny particles that you have created will have multi domains. On the other hand, you have let us say another recipe where you can prepare particles with a very small dimension. So, now we are in this range. So, in this case the magnetostatic energy will not be very high. Actually, it will be lower than the energy needed if we need to form domain walls. Okay. Suppose the system forms domain wall, the energy from domain wall formation will be very high. Okay. So, in this case the system will just do not bother, it will not form any domain, it will exist in a single domain state. So, when you say S D, so it means single domain. Okay. So, when the particle size is very small, the system does not form domains, but when the particle size is very large. So, you can imagine, right. So, if you have very small particles, let us say you may have 1000 spins parallel to each other. Let us say here you have 1000 spins parallel to each other, and if the particle is very very large, maybe you have like 100,000 spins parallel to each other. Okay. So, you can imagine, right. So, this will have large magnetostatic energy. So, it is better they split into domains and minimize the magnetostatic energy. Okay. So, whether the system forms domains or not depends on the competition between these two energy. For large particle sizes, magnetostatic energy is large. So, minimizing magnetostatic energy by forming multi domains is preferred, but for small particle sizes magnetostatic energy is not very high, it is low. So, it is not wise to form domains. So, the system will not form domain, it will be in a single domain state. Okay, let me show some example. So, in this picture you see tiny cylinders. Okay, from side it will look like this, but they are like this. Okay, we have tiny cylinders fabricated by lithography. The diameter of the cylinders is shown here. So, in the first case the diameter of the cylinder is 5 micrometer, second case is 500 nanometer, 200 nanometer, 50 nanometer and so on. Okay. So, we have 4 different cases with a different diameter. So, in this graph, so somewhere here, somewhere here, somewhere here, something like this. Okay. Maybe the 50 nanometer is here, 200 is here, okay, somewhere. So, you look at the 5 micrometer disc. So, you see the brown and say beige color, you see 2 colors. Basically, the 2 colors means in one brown maybe the magnetization is all up, the beige region magnetization is pointing down. Okay. So, you are looking at the domains which are either pointing up or pointing down, and you can see a lot of small lines. Okay. So, that means this system is in the multi domain state. Okay. multi-domain state. Now, we look at another cylinder, all have same thickness, this T is the same, thickness is the same, only the diameter is different. So, now you look at the 500 nanometer diameter region. So, you see here brown, beige color. So, this is one domain pointing up, this is another domain pointing down. So, here you have two domains. In this disk you can see three domains, brown, beige, brown. Here again you see three domains. So, basically 500 nanometer also domains have formed. So, it is still in the multi-domain state. So, when you go to 200, some disks have like two domains, right. So, one brown, one beige, here again like one brown, one beige. Okay. So, this is somewhere here. Okay. Some of these particles form domain, some do not form domain. Okay. But once you go to 50 nanometer, you take all these small regions, either they are fully white or fully brown, right. So, none of them have any domains like this. So, here you see like Pepsi kind of pattern you can see, but here you do not see, here all of them are either brown or black. That means, those small disks are in the single domain state. Okay. So, this is the clear evidence that the formation of domains depend on certain critical diameter. So, if you are above that critical diameter, the magnetostatic energy is high. So, the system forms domains, and if you are below this critical size, magnetostatic energy is not that high. If you form domain, you are going to increase the domain wall energy. So, the systems do not form domains, they exist in a single domain state. Yes. Pardon? Okay, what is super paramagnetic? Okay, this is actually super paramagnetic. Okay, let me go back to the white screen. Okay, so now you are clear with these concepts, right? So, what is paramagnetic? As a function of time. Okay. So, your neighboring spins are randomly oriented and also they fluctuate as a function of time. So, at another time they are random again. Okay, so, this we know, we already learned yesterday. So, super paramagnetic refers to a situation that let us say you have a ferromagnetic cylinder. Okay, you have a ferromagnetic cylinder. So, inside this cylinder you have many spins, right. So, it is a ferromagnetic material. It is a ferromagnetic material, the neighboring spins are parallel to each other, but this particle is too small. Let us say this particle has a very low volume. Okay, either because the diameter is too small or thickness is small. for some reason these particles have very low volume, then what happens is when you have a ferromagnetic particles, the energy that keeps the magnetization in a certain direction depends on KUV, where V is the volume of the particle and Ku is the anisotropy constant of the material. Okay, so, if you multiply the anisotropy constant of the material with the volume of the particle that you have prepared, then you have this term. This is called anisotropy energy. Okay, so, this energy is the one that keeps the magnetization fixed in one particular direction. So, we learnt about permanent magnets, right. So, yesterday there was one question, why the permanent magnets retain the north pole and south pole. That is because those materials have a very large anisotropy constant. So, there is a large anisotropy energy. So, this anisotropy energy is the one that determines whether a material is hard or soft. Okay. Now, let us come back to this particular case. So, you have a particle with a very low volume. So, even if this particle has a reasonably high anisotropy constant, because the volume is small, you can say the KUV is low. Okay. So, there is one energy, anisotropy energy, that tries to keep the magnetization in a particular direction, but at room temperature, let us say 300 Kelvin, we have the thermal energy, which is basically Boltzmann constant multiplied by room temperature. So, there is a thermal energy. Okay. This thermal energy will compete with the anisotropy energy. Okay, so, in the case of paramagnetic materials, thermal energy is the one that makes the magnetization of the individual atoms to fluctuate randomly. Okay. So, similar thing can happen here. So, when this is low and when these two values get closer to each other, the thermal energy may cause the magnetization of this particle to fluctuate randomly. Let us say this is the magnetization of this particle. So, I observe at time t1 magnetization is like this, at time t2 maybe magnetization is like this, time t3 magnetization is somewhere like this. Okay. So, this magnetization keeps fluctuating as a function of time, because the thermal energy starts competing with this anisotropy energy. Okay. So, here when I draw this arrow, I am talking about magnetization of this particle. Okay. But if I zoom this out, the neighboring spins are still parallel to each other. Okay. So, at one point of time, all these spins are like this. Okay. At time t2, all the spins are like this. Okay. At time t3, all the spins are like this. So, what it means? The system is still ferromagnetic. Okay. The neighboring spins are parallel. So, your particle is still ferromagnetic, but the particle magnetization is behaving fluctuating. Okay, particle magnetization is fluctuating as a function of time, like the atomic magnetic moments fluctuate in a paramagnetic material. Okay. So, that phenomenon is called super paramagnetism. So, the term paramagnetism basically refers to this time varying magnetic moment fluctuation. Okay, but here it is still a ferromagnet, okay, because neighboring spins are parallel, but their magnetization fluctuate, the magnetization fluctuates as a function of time due to this thermal energy competing with anisotropy energy. Okay. So, when you are in the super paramagnetic region, the particle will not have coercivity, okay, because they are fluctuating as a function of time. The hysteresis loop will vanish. So, normal case, let us say you measure the hysteresis loop here, you will have coercivity like this, but if the particle size is small, too small, then the hysteresis loop will be, I mean there is no hysteresis loop, particle will be like this. Okay, you can see the particle, super paramagnetic particle still have a large MS. They have a large MS, but they have 0 remanent magnetization and coercivity is 0. Okay, so, this is a huge difference between paramagnetism and super paramagnetism. Paramagnetism MS is almost 0, right, but super paramagnetic material will have a large MS because it is ferromagnetic. Only thing is it does not have a remanent magnetization or coercivity. So, this happens when you make the particles too small, okay, below certain dimension, the particles will be in super paramagnetic limit. Okay, let us do some questions. Okay, majority of you are wrong. Okay, so, domains are formed only when there is a minimization of total energy. So, I told you 2 cases, right. So, if you have big particles, then when you form domain you minimize the total energy, because so basically the answer 3 is the correct answer. So, you also have another case, right, single domain you are not forming domains because you are increasing the domain wall energy. So, domains are formed only when there is a decrease in the overall energy of the system. That is why I told you, I mean not all time we form domains there. Okay, majority of you are right. So, formation of domain walls increases the exchange coupling energy, because your neighboring spins are not parallel, they have certain angle, and because theta is not 0, we have some increase in the exchange coupling energy. So, this is the correct answer. Okay, most of you are. So, if the nanostructures are below a certain critical dimension, they do not form multi domains, this is correct. They are single domains, correct, and they may be even super paramagnetic. If they are too small, they may be even super paramagnetic. So, all of the above is the correct answer. Okay, so now we are on the last topic of magnetism. Okay, so before I start this one, let me ask you a question. Let us say I have a piece of magnetic material. So, let us say this is iron or some magnetic material. Okay. Then I have a magnet. Okay. So, let us say this is north pole of the magnet. I bring this close to the magnetic material. Okay, then there are a few possibilities. Okay, now I am drawing the cross section. Okay, you are looking from this side. Okay, I bring magnetic material. So, you know that this material will be magnetized. Okay. So, this is scenario 1. Only the region directly below the magnets get magnetized. The second possibility is like, even though my magnet is only this small, this whole region from here to here get magnetized by this small magnet. Okay. So, now this whole region is north pole up, south pole down. Okay. So, here this is the influence of my magnet, here this is the influenced region of my magnet. Okay. So, when I bring magnet next to a magnetic material, which scenario will happen, 1 or 2 or maybe either. Okay. So, how many of you are thinking that 1 will happen? Raise hands. No one? Okay, 1, 2, 3, okay, 3, 4 hands for this one. How many of you think that 2 will happen? Nobody? So, I bring a magnet, a wide region gets magnetized. How many of you think 2 will happen? No one? Okay, 0. How many of you think that either of this will happen? 1, 2, 3. So, 23 of you have no opinion. Nota. Okay, so, when you bring a magnet next to a magnetic material, I mean this question, right, nobody teaches in magnetism. So, many of you would have studied magnetism, nobody discusses this one. Okay. And whenever I even interview postdocs for postdoc position, I ask this question, they do not know. Okay. But this was very important aspect. As a magnetism trained person, you should know this. Okay. So, when you bring a magnet next to a magnetic material, this can happen, this can also happen. Okay. Either can happen. So, it depends on the state of your magnetic material. Okay, so, we learnt about single domains. So, in some cases we learned that the system will have no domains, all the tiny particles will be in single domain state, and we learned that in some system we will have multi domain states. So, depending on whether you prepared a system of single domain particles or whether you have prepared a system of multi domain particles, either can happen. Okay. So, in the case of single domain particle, this one will happen, okay, this phenomenon, where only the region directly below the magnet will be influenced by the magnetic field. Whereas, if you have prepared a multi domain system, even you bring a magnet, a large region even beyond the influence of magnet will be affected. Okay. So, this aspect of how a magnetic material responds to the applied magnetic field. It is called magnetization reversal mechanism. Okay. So, how a magnetic material responds to a magnetic field is called magnetization reversal mechanism. So, it can happen through many possible ways. So, one mechanism is called domain wall motion. Okay. So, this is one type of reversal mechanism. Then another type of reversal mechanism is called coherent rotation, which is proposed by these two scientists, Stoner-Wohlforth. So, it is also called Stoner-Wohlforth reversal mechanism. Then there are also some other more complex reversal mechanisms, but let us just stick to these two reversal mechanisms today. One is the domain wall motion, the second one is coherent rotation. So, as this slide implies, coherent rotation happens when you have a system of single domains, and when you have a system of multi domains. Domain wall motion is the dominant reversal mechanism. Okay, you do not need to read through the text. Let us say you have a system where you have many domains, a magnetic field along this direction. The region where the magnetization is pointing in the same direction as the magnetic field expands. So, you can see that this region has expanded. So, initially the domain wall was here. Okay, you can see that this domain wall has moved. Okay. So, the domains which are in the same direction as the applied magnetic field, they expand. Okay. So, this kind of reversal mechanism is called domain wall motion. Okay. So, you can observe in this video. So, here let us say black means the magnetization is going into the board, gray means magnetization is pointing towards you. Okay. So, this video is taken using curve microscopy in my lab. So, we can observe the domains, domain wall motion and so on. Okay. So, you can see when we apply certain magnetic field, these domains expand. Okay. So, the black domain expand. So, this is the domain wall. Okay, at this point of time, this is the domain wall. You can see the domain wall expand, and at this point of time the domain wall is here, and you can see the domain wall moves, right. So, this is the domain wall motion reversal mechanism. So, normally when you make, let us say you are making thin films, let us say you are depositing thin films, right, without any special technique. Let us say you deposit a piece of cobalt film or any film without some special technique. So, this film usually forms the case where you have multi domains. It is quite common to form magnetic material into multi domain state. So, if you want to form single domain states, you have to make the particles too small, or you have to employ some techniques to achieve single domains, but the default case is that when you deposit a magnetic film or prepare some magnetic material, it always form multi domains. Okay. So, when you have such films, the reversal mechanism is always domain wall motion. Okay. So, this is what I meant. The reversal mechanism depends on the state of your film. So, if your film or sample has multi domain state, then you will have this domain wall motion reversal mechanism. Okay, so, when you have a film, let us say you have a film so, within this film, due to the composition inhomogeneity or something like that, you may find some regions where the energy is different, energy landscape is different compared to the rest of the region. So, for example, this region A, the energy is low, region D, the energy is low. So, when a material is like this, usually when the domain wall comes here, it will get stuck. Okay. If you apply some more energy, the domain wall will be released from here and maybe it will go here and get stuck. Okay. So, some energy minima in the system will stop domain walls and we call them as spinning sites. So, these are common features of domain wall motion. And if you have studied Barkhausen noise, this Barkhausen noise comes because the domain walls are getting stuck at many pinning sites and they get released and so on. Okay. Now, let us come to the second point. Second point is another type of reversal mechanism called coherent rotation. Okay. So, this happens when you have a system of single domain particles, which means your particle size is small. So, within that particle you do not have domains, it is a single domain. Okay. So, what happens to the magnetization of the particle when you subject them to magnetic field was studied theoretically by these two scientists, Stoner-Wohlforth, and they propose how they will, these particles will reverse their magnetization when they are subjected to a magnetic field, and this model is called Stoner-Wohlforth reversal model. So, here they undergo coherent rotation, which means when you apply magnetic field, let us say initially all the spins within this particle are parallel pointing like this. Let us say you apply magnetic field in this direction. So, when they go from up to down, so at some point of time maybe all the spins are like this. Okay. At another point of time they may be all like this. So, you can see that they are all coherently going together from one direction to the other direction, like the synchronized swimmers they do in Olympics. So, they all behave like synchronized to each other. Okay. They go coherently from one direction to the other direction. Okay. So, this is what it means, all the spins rotate together with respect to the external magnetic field. Okay. So, according to this Stoner-Wohlforth reversal mechanism, let us just highlight the results rather than the derivation. So, if you measure the, let us say now we are taking just one particle. Okay. So, we take one imaginary particle, let us say it has the z axis along this direction, and I apply, let us say magnetization is initially in this direction, I apply magnetic field in the opposite direction. Then this particle, initially it was like this, once I apply reverse magnetic field, it reverses to the other direction at a field called H k. H k is called anisotropy field. Okay. So, again now this particle is down, so I apply magnetic field in the other direction, it goes back to this state at the same field H k, and the value of H k according to the Stoner-Wohlforth reversal model is given by this. So, K u is the anisotropy constant of this material. So, different materials have different anisotropy constant. So, depending on the anisotropy constant of the material and the m s, this H k will be different. So, some materials like iron, platinum have H k as high as 7 Tesla. Some materials like say cobalt, platinum alloy for example, they may have 2 Tesla H k. So, depending on the K u and m s, this H k may vary. Okay. So, but the important point is that the reversal happens at this field. So, when the applied field is more than this 2 K u over m s, the particle will change from one direction to the other direction, that is in the easy direction. Okay. But if you apply in the hard direction, the magnetization will slowly rotate. So, initially magnetization is like this, you are applying magnetic field in the hard direction. So, the magnetization will slowly rotate at some field. So, when the field is more than H k, the magnetization is completely pointing in the direction of your applied field. Okay, but once you remove the magnetic field, it will come back to the easy direction. Okay, this is what we learned before also. Okay, so, in the hard direction, there is no hysteresis loop. So, when you take a single particle under Stoner-Wohlforth model, there is no coercivity in the hard direction. Okay. Remanence is 0, coercivity is 0. This one is a theoretical model. Okay. Theoretically, if you take one particle, it will have 0 remanence, 0 coercivity when you measure hysteresis loop in the hard direction, but you notice the m s is still the same. Okay. So, this, if you remember, I asked you one question whether m s is same or not. So, m s is the same. Okay. In the hard direction, when you apply field more than the anisotropy field, the system will go to the saturation magnetization. Okay. So, this is the easy direction, hard direction. What if you apply magnetic field along certain other angle like 30 degree, 60 degree, the hysteresis loop will look like this. Okay. So, this is one way of explaining what happens to a Stoner-Wohlforth particle when you apply magnetic field. Okay. So, let us say this particle has a easy direction along this one. So, the magnetization can point like this or like this. Okay, there are two possible states, one is magnetization pointing this direction or magnetization pointing in this direction. So, those two are the lowest energy states. Okay, so, you can see that let us say this is called energy landscape. So, you plot energy as a function of the angle between the field and magnetization, angle between the easy axis and magnetization. Okay, so, when the magnetization is parallel to the easy axis, parallel or anti-parallel, the energy is low. And as I mentioned, if the magnetization is pointing 90 degree with respect to the easy direction, energy is high. Okay, so, this is the energy landscape when there is no magnetic field. Okay, when you do not apply any magnetic field, this is the energy landscape, and this value is called energy barrier. That means, the difference between the lowest energy and the highest energy is the energy barrier, and this is what is called KUV. I already described before. When I discussed super paramagnetism, I talked about this energy barrier KUV. Okay. So, all single domain particles according to Stoner-Wohlforth model have an energy barrier E b given by this expression. So, it depends on the volume of the grain and the anisotropy constant K u of the material. Okay, now, let us say you apply some magnetic field, you increase the magnetic field. So, when it is close to the coercivity, you can see the energy landscape has changed. This direction, this one has the lowest energy, and this is a excited state. And once you reach a field closer to the coercivity, there is no energy minima here. Okay. So, the particle cannot exist here, it has to go to the energy minimum. So, this is where it switches from magnetization pointing up to pointing down. Okay. So, when the field is more than the coercivity, basically there is no energy minima, particle will switch. Okay. So, this is the concept of Stoner-Wohlforth reversal mechanism. It is lunch time, right? Let me see whether there is anything very important. Okay, there are some questions and okay, there are some questions to be asked. So, maybe let me ask those questions as a recap during tomorrow's lecture. Okay. So, we will stop here, we will go for lunch, then we will continue from where we left.